Hi, welcome to Chapter 2 on Forces and Newton's Laws of Motion. In this first part of the lecture, we will look at an introduction to forces. Chapter 2 is broken up into 4 parts. In this first part of the video lecture, we'll look at an introduction to forces. In Part 2, we'll look at Newton's first law of motion. In Part 3, we'll cover Newton's second and third laws of motion. And finally, in Part 4, we will look at centripetal force. No introductory physics course would be complete without covering the accomplishments of Isaac Newton. He is arguably the greatest scientific genius that ever lived. His story is fascinating, as he survived a pandemic that shut down Cambridge College in England in 1665 for several years. The Great Plague, which swept through England, killed 20% of London's population. During this time, Isaac Newton took refuge in a countryside cottage for 2 years and underwent an intense period of self-study and discovery. His mind was free from teachers telling him how to think and what to think about. During these 2 years, his accomplishments were numerous and revolutionized physics and mathematics. Here's a short list of what he did. He discovered 3 laws of motion, which will be the topics of parts 2 and 3 of this chapter's lecture. Some of the problems that he worked on were actually so difficult that they were unsolvable by the mathematics that were available to him at the time. So instead of giving up, what did he do? Well, he invented calculus as a tool to solve physics problems. Newton discovered the law of universal gravitation. This will be the subject for a future chapter in our course later on this semester. He discovered several different laws of optics, and he also invented a reflecting telescope that uses a curved mirror instead of a lens, and every professional astronomical observatory in use today uses a reflecting telescope originally designed by Newton. So this is an important milestone in our course here. We're changing gears here. We're going from the study of kinematics to something called dynamics. In kinematics, remember the definition of kinematics is a mathematical description of how things move. So in the previous several chapters, you learned a bunch of mathematical formulas and equations that describe motion. You learned about velocity and displacement and acceleration, and learned how to do various problems involving projectiles and objects moving and so forth. However, none of those problems dealt with the causes for the motion. What made something accelerate? Why did a projectile move the way it did through the air? So this is where we now basically start the real physics of this course. And we switch gears and talk about what is called dynamics, the study of why things move. And one of the key concepts of dynamics is cause and effect. And this will be one of the concepts that we will investigate, particularly in parts 2 and 3 of this lecture. The key concept to Newton's laws of motion is the concept of force, because forces are the reason that things move. Isaac Newton discovered that forces are the cause of motion. So a definition here, what is a force? Well, it's actually very simple in concept. A force is anything that pushes or pulls on an object. So there are almost countless examples of using forces, and you can probably come up with several more. But for example, if you think of examples of pushing force that you might have used perhaps today, pushing a shopping cart. When you walk or run, your feet are pushing against the ground, and the ground is therefore pushing you forward. When you throw a ball, you're pushing the ball with your hand. When you type at your computer or text on your phone, you're pushing the keys with your fingers. Even when you write with a pencil, you're pushing a pencil, as they say. So that's a short list of pushing forces, some examples of pulling forces that you are certainly familiar with. When you open a car door or your refrigerator door, you're going to be pulling open the door. When you pull on a rope, obviously you're pulling. Stretching a rubber band is an example of pulling. Any muscle motion or movement of your body is ultimately due to a muscle inside your body contracting. And when a muscle contracts or shortens, it pulls on the bones that are attached to, and that's what causes movement. A chandelier hanging from a ceiling, the cable that is holding the chandelier is pulling on the chandelier with a force called tension. So here's again, this is just a short list of pulling forces, and I'm sure you can think of some more. We can start to classify forces to make some sense of them. And one way to do this is to think of them as either contact forces or long-range forces. So what is a contact force? Well, here are some simple examples that are easy to visualize. When you push a chair, your hand is obviously making contact with the chair. When you pull on a rope, again, there's direct contact between your hand and the rope, or the rope and whatever the object is attached to the other end of the rope. When you hit a baseball or a tennis ball or something like that, you're making direct contact with the ball. Now, other forces are examples of what are called long-range forces, and long-range forces work at a distance without any direct contact. So the most familiar one, of course, is the force of gravity, the gravitational force. So as we see this ball bouncing up and down, the ball is being pulled downward towards the earth by gravity. And notice that, the earth is not in contact with the ball until it hits the ground, of course. But while the ball is falling, gravity is pulling the ball downward towards the earth. The magnet over here, if you've ever had a chance to play with magnets, they will attract iron objects from a distance. And you can pick up nails, or anything made of steel or iron from a distance, depending on how strong the magnet is. And another force, that we're not going to really be dealing with in this course, but if you take Physics 102, you will, that is the electrostatic force. So in this example here, we have two objects with opposite charges. One is negative and one is positive, and they are attracted to each other. And this electrostatic attraction is a force at a distance, because again, they are attracted to each other from far away. They don't have to be touching to be attracted to each other. Force is another example of a vector. Remember that vectors have both a magnitude and a direction associated with them. So for a force, the magnitude of force is the size or strength of the force. And we can represent this by the length of the force vector. So in this image here, we see the woman pulling on a rope connected to a crate here. So we can represent the force, the tension force in the rope, we can represent it with a vector diagram like this. And this arrow represents the pulling force. And obviously we draw the arrow pointing in the direction that the force acts. So from the crate or box's point of view, we have the rope pulling it to the right, so that is the direction of the tension force acting on this box here. One of the forces that we will be dealing with in almost every problem that we work with in this course is the force of gravity. The force of gravity is called weight. So weight is by definition the force of gravity that acts downward on an object. So if we have an apple here and it's falling, let's say, we have a downward force due to gravity called weight. And of course, the arrow for gravity, the force of gravity, is always directly straight down, no matter what direction the apple is moving in, or even if the apple is hanging in the tree, it still has this weight force pointing downward. You can visualize weight either by doing a thought experiment or actually doing, lifting things at home. But for example, when you lift up your pencil, you can feel the weight of the pencil on your hand, and obviously that's a relatively light object. The force of gravity is very small. If you lift a book, or think of lifting up a heavy rock out in your yard, the force of gravity is going to be much greater there, and you can very easily feel that weight due to gravity of the heavier object. There's our apple falling, by the way, a little animation. And again, we're going to learn about the cause and effect of forces in parts 2 and 3 of this video lecture. But again, the key thing here is the force of gravity. Because it's down, an object, when let go, will fall straight down due to the influence of that weight force pulling it down towards the earth. So take a look at this situation here. We have an apple resting on a desk. So think about what forces are acting on this apple. And for a hint, think about the question, why doesn't the apple fall? So you might want to pause this video right now and see if you can list or jot down the forces that you think are present that are, remember, a force is anything that pushes or pulls on the apple. So the reason the apple doesn't fall, of course, is that the table is pushing up on the apple. So the apple has a weight force pulling it down towards Earth, but the table is a force pushing it up. And we call this type of force a normal force. It's sometimes also called a support force. So a normal force, by definition, is a force exerted by a surface in contact with an object pressing against the surface. Normal means perpendicular here. It's a mathematical term. Normal means at right angles to the surface. So if the tabletop is horizontal like this, the normal force is going to be vertical and pointing upwards. And of course, a normal force is a contact force. It requires contact between the object and some surface, whether that surface is the floor, a table, or if something is leaning up against the wall, the normal force can be the wall pushing outwards on the object. Now, one thing we're going to do here, and this is an important step forward for us in this course, is to take a situation like this, a physical situation where we have an apple resting on a table, and we are going to represent the forces with arrows in something that is called a free body diagram. So what we do in a free body diagram is we only show the apple. The table has been replaced by the effect of the table, which is the normal force pushing up on the apple. And the earth underneath, of course, is pulling down on the apple due to gravity, but we don't have to draw the earth. Instead, we just label and draw this arrow with the weight force, the force due to gravity, pointing downward. So this is an equivalent picture to this situation over here, and it's much more easy and efficient and convenient to draw than having to sketch out this whole thing. Now, oftentimes, especially in your book, they will represent the object, like the apple, with just a dot or a circle, and that's fine as well. The other thing, notice here is that the position of these arrows on the object is not important at this point in time in this course. The only thing that's important is the direction. So notice in this picture here, I have the weight arrow on top pointing down. Over here, the weight arrow is underneath the object, but the important thing is it's pointing downward. So that's all we care about. It doesn't matter where this arrow actually is. Likewise, the normal force points up. We can either show it underneath the object here, or equivalently, I can put the arrow up here, or in this picture it's shown, again, on top of the object. The key thing is the normal force points upwards. So again, this is the idea of what's called a free body diagram. The body, which is the apple, is basically been drawn free from everything around it. The only thing we have to do, and we have to be very careful when we do this, is label all the forces and put their correct orientation. In other words, which way do these arrows point? So suppose you take a box and slide it across your kitchen table. What do you think is going to happen? If you don't, let's say we don't push it hard enough so it actually flies off the table. Let's watch the animation here. So we see the box come to a stop, right? It slows down, it's decelerating, obviously, and it actually comes to a stop. So the question is, why? Why does it come to a stop? What is causing the box to stop? So again, if you need to pause this video, think about that. What might be causing this? So the answer, of course, is friction. Friction is a resistive force that acts against the relative motion of two bodies or substances in contact with each other. All right, so when we had our box sliding across the table, friction pushed in the opposite direction as the motion of the box and slowed it down. So friction is, you can think of it as a pushing force. Likewise, if you take a box or a book, you can do this right now at your table where you're sitting. If you push the object across the table, just slide it slowly across the table, there will be a force of friction opposing your motion. So if you're pushing the box to the right, the friction force points to the left. We always know which way friction points. The direction of friction is always opposite to the motion. So the free body diagram for this situation here, this little experiment that you can do right now at home, is shown here. We have weight going down, normal force going up. We have a push force going to the right. That's from the person's hand. And then, of course, friction opposes that and goes back to the left. So this free body diagram now is showing 4 different forces acting on this box. You're probably familiar with a fun game to do at picnics or whatever called a tug of war. Maybe you've even competed in a few of them over your years. So look at our little picture here. We have a tug of war going on with 2 teams of 2 equal competitors on each side. All right, so we're going to assume these guys are all the same size and strength. So the question here is, why doesn't the box move? So why does nobody win this tug of war? They're all pulling, obviously, right? So think about your answer to this question, and then you can pause the video, and then we'll continue on and we'll talk about this. To answer the question, why doesn't the box move, brings up the next concept, which is that of net force. So what is net force? Well, net force is the equivalent total force due to one or more forces present. So in this case, we obviously have these 2 guys over here are trying to pull the box to the left. So they are producing a force to the left. On the other hand, these 2 guys over here are obviously pulling the box to the right. And since they're all pulling with the same amount of force, when we add up their forces, the force of these 2 guys is canceled by the force of these 2 guys. This means the net force is 0. So net force is going to be a key concept when we study dynamics, especially when we, again, look in parts 2 and 3 of this chapter. We're going to be dealing almost always with the idea of net force. The net force is the important force because it is what is going to cause an object to either move or not move. So let's look at our tug of war again, and let's change the situation a little bit. Let's add a third player to the team on the left. So let's go ahead and watch the animation here. So now we've got these 3 guys are pulling against these 2 guys, and you saw what happened. All right, since there's 3 people over here, obviously they're going to be able to pull with more force than these 2. So there is a net force pointing to the left. We no longer have a net force of 0. We now have an actual net force, and it points to the left. The other thing we can do here is we can think of the equivalent net force. Remember that this guy right here cancels out this one over here. Likewise, you can think of this guy here canceling this guy's force, but this third competitor over here has no one over here to balance and cancel his force. So the equivalent net force on this box is the same as if just one person was pulling this box to the left. Since we're going to be measuring and using force in solving problems later on in this chapter, we need to quantify force. And so we need a unit of force measurement. So force in our class is measured in newtons, named, of course, after Isaac Newton. So the symbol for a newton is an uppercase N. So 1 newton, by the way, is equal to about 1/5 of a pound of force. So a newton is a relatively small amount of force. About 5 newtons is what's required to lift up a 1-pound object, like say a textbook or something like that. So let's go back to our example down here with our tug of war, and let's suppose that each man is pulling with a force of 500 newtons. So on this side, this team, we have 3 guys, each pulling with 500 newtons. So their force to the left is 1,500 newtons, 500 times 3. The 2 guys on this team, on the right side, are pulling to the right, of course, with 1,000 newtons, because each one pulls with 500 newtons. So this is a free body diagram for the box, just including horizontal forces. I didn't include gravity and so forth, but we're just interested in the horizontal forces here anyway to see who wins the tug of war. And you can see, obviously, that we have much more newtons of force here on the left side. Now, we can even simplify this a little bit more. We can add these 2 force vectors together. We have 1,500 to the left. We can take away 1,000 because it's going to the right. We're going to subtract these forces, not add them. And we end up with a net force of 500 newtons pointing to the left, which again is the equivalent of one human, one of these guys pulling, because the other 2 are canceled by the guys on the other team.